Welcome back to the second part of the challenge overview. This video will be a lot more theoretical. We'll dive deep into the math behind this challenge, and we'll also go over a potential obstacle that you might face within this challenge. So we turned a vague problem of how do you accumulate as much Bitcoin as possible into a machine learning problem in the previous video, and that is what the Stacking Sats challenge is all about. Diving deeper into it, what we really did when we said let's abstract away the dollar denoted budget to a budget that's normalized to 1, and let's use that to represent our entire budget, a complete portion, and we're going to allocate a amount to purchase every day over some duration, which we called an accumulation cycle of 4 years. So we're saying that we're accumulating over all n days in that accumulation cycle. We turn this into compositional data. So compositional data is data that comprises of quantitative descriptions that sum up to a whole. And in this case, it sums up to our entire budget. And this sort of data has a very interesting geometrical representation. So the mathematical way of representing this is through a simplex. Now I'm just going to skip over here to show you the simplex. This notation here represents a n-1 dimensional simplex, and all it's saying is that in our case it's the set of all vectors, all weight vectors. So this W in the set of n-dimensional reals is exactly this here. We have a weight for each day in our accumulation cycle. We have, because we said there's going to be n days in that accumulation cycle. And we have the exact same constraints from the previous part of the challenge, where each day we have to purchase some minimum amount, and we must use up our entire budget over all those days. So all our WIs should sum up to 1. Now, this is the interior of the simplex, hence this notation. Think of it as the clipped simplex. And because it sums to 1, it's denoted and it's referred to as a standard simplex or a probability simplex. But those were just details in terms of what this problem really is. Once we dive deeper into it, it will become handy later on. Now, we can think of a uniform strategy as simply a point in that simplex. It's simply the point that has all its allocations as 1 over n, hence the word uniform. If you were to plot its weights over all the days, over all n days, it would just be a flat line. But regardless, we were thinking about this problem as a mapping, that what we want to do is we want to think of a model that provides us an informed decision based on features that enables us to make an informed decision for generating weights. And now we have a very concise and beautiful way of talking about the feasible region, which is this simplex that we spent so much time talking about so far. Nothing new so far. And we spoke about this mapping as this unconstrained optimization in the previous video as well, which we said that we care about the Satoshi per dollar, which is defined as this, where PI is the price of Bitcoin, or specifically, I believe it's the closing price of BTC on day I. And what we really want to do is we don't want to cherry pick our weights to find the best outcome. We want to find models that map features to those weights that are optimal. And that's what all this is about. There's just this quick note that in the previous overview video, we spoke about maximizing the Satoshi per dollar percentile, which is over here. And here we're talking about maximizing Satoshi per dollar. But they're mathematically equivalent. Over any window, the worst and best SPD are fixed. So in order to find the optimal point of SPD percentile, it's equivalent to the optimal point of strategy SPD. So that's all the stuff that, again, is not new. This is just going over it in a more precise way, or rigorous way, formal way. The thing that's important is that when we formalize our problem this way, when we ensure that our models adhere to this sort of structure, it ensures that we avoid any sort of hindsight bias, because it becomes obvious that you should perhaps buy at this day or that day when the day has already occurred. And it's quite obvious that you should have bought Bitcoin, let's say, all the way back in 2010 when it was less than $1. But that isn't really useful for us today. So when we ensure that we are making these decisions based on models, perhaps those models provide us interesting results, and it shows that we beat the regular dollar cost averaging approach across historical data. So perhaps we can now generalize it and extrapolate that to new data and essentially use it in practice. Now, also, when we talk about the problem that was very vague to begin with, how do we accumulate as much Bitcoin as possible? Now, when we talk about the simplex and saying that you should map your features into this feasible region, we're able to create a challenge out of that. Now we could do direct apples to apples comparison and see which accumulation strategy does better and which one does worse. I think a very important point is when we're deriving these features and we're thinking about which features to use, how our model should use those features, what we're really doing is that we're unveiling structural properties and characteristics about Bitcoin. Perhaps you're uncovering certain points about how volatility clusters, or you're uncovering certain seasonal aspects of Bitcoin that you're later using and leveraging to improve accumulation. So we're actually pushing our understanding of Bitcoin forward by being able to beat a dollar cost averaging strategy. That's almost a prerequisite, that in order to beat dollar cost averaging, perhaps you need to know something about Bitcoin. This is the obstacle that I said we will address. It's that we want you to have models that output results in a feasible region, namely that probability simplex. But one of the constraints is that your model should not be forward-looking. And to break down this mapping, let's talk about this mapping here. Where is it? When you're mapping features to the feasible region, you might think about it in two steps, which is, I want to think of a feature to denote some aspect of desirability. So rather than having these weights, which are actually already inside the feasible region, namely they sum up to 1 and each one is greater than or equal to the minimum weight, perhaps you think about your feature giving you some raw desirability. So these conditions might not necessarily be true. What do I mean by that? Let's say your feature of choice is the 200-day moving average of Bitcoin price. Then you have some idea initially that when price is below the moving average, the 200-day moving average, then perhaps this will dictate some level of desirability on each day. So this could be stage one. Stage 2 then becomes, well, I have a budget to adhere to, and even if I can observe my feature, which in this case is the 200-day moving average, how do I ensure that I make the informed decision from the feature, which might tell me that, hey, the Bitcoin price is well below the 200-day moving average, I should buy quite a bit. So perhaps weight 1 tells me that the desirability is 80, and then weight 2 tells me the desirability is 150 or 160. All that tells us is the relative magnitude, that weight 2 is twice as desirable as weight 1, and that's perfectly fine. But what we have to consider is to get this to be a valid model and to output a result inside the feasible region, we need them to sum up to 1. So you might say, okay, well, stage 2, let me just take each raw weight and divide it by the sum of raw weights, and that will normalize everything, and now we'll be within the feasible region. But then your model is now forward-looking, and you've leaked information from the future, because the whole assumption is your weights are being generated by features, and that means that, let's say, at any day k, you shouldn't really know what your final weight k plus 1 through n are, because then that uses features from day k plus 1 all the way through day n. This is the obstacle that we're really dealing with here. So what we're going to do is provide a template for how you can avoid forward-looking models, but still provide a model that outputs results in the feasible region. And the way to do that is to initialize your weights as a uniform weight. And this is the whole aspect of really enforcing and emphasizing the fact that this data is compositional. It becomes very difficult when you start tweaking each element of the cycle, each day in the cycle on its own. But when you think about your model as spitting out the entire whole at any day in time throughout the cycle, then you can enforce that you always have a vector that's inside the feasible region. So you start off with the uniform vector, which of course is within the feasible region. Then what you do is you take this Bayesian approach, which you, on any day I, you can update the allocation based on all the features up to day I, and also based off what your previous weight vector was. So starting from day 1, we observe the feature at day 1, and we know what we initialized our weights to be, which is just the uniform weights. And we map that to our new weights, and we update that. And we do so in a manner that is, of course, within the feasible region. So that means if we observed a feature that told us that we should buy more because we observed a signal that tells us to buy more based on our model, then you have to do some sort of rebalancing where perhaps I can boost the first uniform weight and add some excess amount to it or scale it up. But now the remaining days, the remaining n-1 days must essentially be scaled down to equal out the new information. Essentially the vector should not leave the feasible region after your update. And the same thing goes for day 2. Now you can observe not only the feature from day 1, but also the feature from day 2, and you make your informed decision by updating your previous vector, WI, your previous weight vector. And you keep doing this all the way to day N. And finally, you say that this is my final decision. This is my final output, which is this final weight vector, and it's going to be inside the feasible region. This is always forward-looking because at any day I, you're only using features up to day I. And it's adaptable. You can think of any sort of function, any sort of model to be applied here. It doesn't assume any specific type of model. In terms of leveraging this, I would strongly recommend using this as your template for thinking of this problem. And if you have a better way of doing it, then feel free to do so. So we're not trying to enforce this template. We don't want to add too many constraints on the search space for these models. It's just something that we strongly recommend to pay attention to. And you will encounter this in a less formal way in the strategy development tutorial. Now, lastly, this is just some cool facts about this whole problem and the geometry of this simplex. Because our objective function, which is the Satoshi per dollar metric, because it's linear, then its unconstrained maximum over the simplex, specifically not the simplex that we're using, which is, I don't know why I scrolled all the way up, it's right here, which is the interior, over the closed simplex. So the only difference is now we actually allow each day to have a daily purchase amount of 0, is going to lie on a vertex. So this is the trivial answer that we were talking about in the previous overview video. If we didn't restrict ourselves to the interior of the simplex, namely saying that the weights must be strictly positive, and in fact greater than a certain positive threshold, then the solution is to go all out and buy all your Bitcoin on the day with the lowest price. And that's the problem of perfectly timing the market. So this is one reason that we do this. This is the formal explanation of why we do this. And one other cool property is that because this feasible region, this simplex, in fact, regardless of the closed simplex or the open simplex, it's a convex space, then any solution can be, we can take any two valid solutions inside this feasible region and think of some linear combination of them such that the parameters sum up to 1, and that will also be a solution. So why is that interesting? So if you come up with two models and it's really hard for you to decide which model does better. Well, in the case of a pure backtest, that will be quite obvious. But in a rolling test, when you're actually looking to use this in the real world, perhaps you could do some equal weighting of model 1 and model 2, and that will also be a third valid model. So that was just a more quantitative overview of this problem. Hopefully it made the challenge a bit more interesting. If not, if it only confused you even more, then try not to think about this part too much and just stick to the challenge overview up here. Now in the next video, we'll start going over the actual development of these strategies. So we're going to move away from theory and start coding our strategy. Thanks for watching.